Of this video is to give you a quick introduction over the X-ray fluorescence calibration software that's available online. The base idea behind this is to use reference standards to form what are called empirical calibrations. Now, what this means is that we'll use empirical standards to get quantitative values. The reason this approach is preferable to some is because the same corrections you do on one instrument can be applied to another, which can help make them agree with each other and help form the basis for both reliability and interlaboratory comparisons. Now, our first step is going to be uploading spectra. Now, real quick, right now you can upload two kinds of spectra. First, our spectra CSV files, and the other are net counts via Bayesian deconvolution. We'll be revisiting and seeing if we can add new file formats later. So we'll go to choose spectra. We're going to go to instrument 1864. And we're going to grab the Mudrock reference set. Now, the Mudrock reference set is, they're basically clays from geologic cores, and they form a nice general set of calibration curves for silicates. So MS15BL, we'll be doing the major sequence. So in other words, this is geared towards lead elements like magnesium and sodium. So let's grab those. There's about 26. Process data, and then let's name it T4. S1864 Mudrock Major. Now, real quick, if I click Plot Spectrum, we can actually view the spectrum in the app itself. This way, if you have a question about what corrections to add or any other edits to make, you can always refer to the spectrum and zoom into a portion of it, which we'll do right now. It's not the best spectrum analysis software around, but it'll at least give you an idea of what you're looking at when choosing corrections. If we come over to counts, this will produce a table of photon counts. Now, what that means is for standard MS15BL122, we've got 2,771 counts per second of calcium, 407 counts per second for titanium, and etc. What we'll want to do is add in sodium, magnesium, aluminum, silicon, phosphorus, sulfur. We're going to add chlorine. We don't have values for chlorine, but we do have corrections we can use it for. Choosing an element here just means you can use it as an option later. It's basically a first pass. And then we're going to go up to iron. Now, a couple L lines we'll want to add. The first, and I just kind of put this in your default, would be rhodium L alpha. You could also do rhodium K beta. The reason for this is because these lines, in fact, we'll add rhodium L beta too, just in case, but these can be corrections we can add later on. For light elements, because we're only doing 15 keV, the rhodium L line is sufficient, but if you're doing 40 keV or higher spectrum, then the rhodium K alpha and beta lines are ones I would add as well. We're also going to add barium L alpha. So now we've got a full table of counts. We will confirm those elements and come over to add concentrations. Now here, we just need to paste in known values. One thing to highlight, you can choose whatever unit you want. So I can do part per million. We can do Oompa Loompas per square kilometer, or cubic kilometer, whatever you would like. In this case, weight percent will be sufficient. So first things first, let's import values. Now you may not be able to copy the whole spreadsheet over. In this case, I'm going to stop at sulfur since I have no values for chlorine. Now, one thing to note, the software automatically organizes everything in order of its atomic number and energy of fluorescence. So you'll see a K sequence and then an L sequence. Next, let's add in potassium through titanium, and then chromium through iron. And then finally, we've got some data for barium. We'll add that in. Now, quick note, maybe for some values, for example, iron up here, maybe we don't have confidence in that value. If you put in any alphabetic letter, it'll automatically delete that value. So anything non-numeric, it'll take it out as a blank, and it'll remember that blank. That said, I don't want to do that for iron, so we're going to go ahead and copy and paste that value back in. Next, we're going to click Enter Values, and then come over to Calc Root. So you might see a couple errors when you start. That's fine. They'll pass quickly. So first things first, let's orient ourselves in the software. Here, we can choose a list of elements we'd like to analyze. We can choose calibration curves. There's linear, which is y equals mx plus b. Non-linear, which will provide which will be a quadratic regression, and then a Lucas tooth regression, which is where we can add intercept and slope variables. Now, for normalization, you can normalize by time, which the software does automatically. We can go to total counts, which basically sums all the photons together and then looks at iron as a fraction of that total. Now, if you do that, you'll want to restrict that type of analysis to metals, salts, crystals, or anything where you have complete information for the spectrum. Now, what do I mean by complete information? Well, if we use X-ray fluorescence on clays, like we're doing right now, the number one element, both by weight and by atomic abundance, would be oxygen, which we can't measure. So total counts doesn't help us that much because one of the biggest variables we can't measure. And then finally, we have Compton, which is here very loosely defined as a region of the spectrum we like to normalize to. Strict physicists will lecture me on noting that the Compton peak is restricted to 18.4 to 19.5 keV with rhodium, or that'll change based on the X-ray anode source or target. But here, it's basically a range of the spectrum. So you can use Bremsstrahlung, you can use background values, you can really use anything you want. Now, for sodium, if we look over here, we've got a calibration curve, which is facing down, which means it's negative, never a good sign. But what we have here is the x-axis, which is sodium counts per second. And then on the y-axis, we have the concentrations of sodium. And then up here, we've got a little equation, which tells us an R squared of about 0.15, which isn't great. And then we've got our equation here. This equation, when you do Lucas tooth, unfortunately doesn't do a good job of updating. I'll look at changing that in the future, but it's hard to make an equation that changes based on your inputs. Now, if I come over here, I've got my calibration validation plot. Now, what that means is I've got my sodium estimate in weight percent on the x-axis, and we've got a sodium known concentrations on the y. Now here, we expect the R squared to be pretty close to what you get over here, though when you start doing Lucas tooth, that might change just a little bit. But we want to see a higher R squared value. But here you'll also want to see a slope of 1. What that means is this for every 1% increase in my estimate, I've got a 1% increase in my known. So a 1-to-1 comparison. Keep an eye on that. I've designed the algorithm so you can't really make a mistake egregious enough to cause deviation. Though if I go to total counts, and let's say Lucas tooth, and then let's add a random intercept, you might start to see some deviation there. Although apparently I'm really good at this because I can't even break it then. In any case, but let's try subtraction. You can kind of see it there. The dotted line is basically going to always be your 1-to-1 line, and the blue line will reflect the true value, so to speak. Yeah, I've made that really robust. I'd love to be able to show you, but I might not be able to break my calibration enough. We'll see if we'll revisit that later. If you want to get rid of these corrections, you can just delete all the way through. Oh, we need at least one slope, and we'll put that for sodium. All right, so in any case, let's go back to linear, let's go back to time, and let's look at our base equation. That is our calibration curve plot, calibration validation plot. You'll notice a couple other tabs here. The first is Diagnostics. Diagnostics may hesitate a bit to load, but it actually provides you a lot of useful information. It gives you statistical plots that kind of give you a sense of the performance of that linear model. I don't want to get into the details of what all these mean here, but these are by and large standard diagnostics used to evaluate regression models. In general, for the left-hand side, you want all these blue lines to be flat, and you want all the points to fit within the gray shaded curve, which is our standard error. And then over here with our standardized residuals, you'll see that the more troublesome the point, the larger it is, so that way it'll be very obvious. Our normal QQ plot, the goal is to make our points fit that line as closely as possible. Cook's distance just tells us which values are a little bit high. And then finally, our leverage plot kind of gives a sense of outliers. Now, quick note on outliers. Statistical outlier is also discussed as just a value that hangs out further than the others. For example, some would argue this point over here would be an outlier. I would take a much more cautious approach because An outlier strictly should be something where the known value is incorrect. In other words, an invalid value. An outlier is fine if it really represents a real measurement. But as anyone who's worked with ICP-MS or neutron activation analysis or any other quantitative chemical approach knows, we can have problems with that get passed on to the elements. So you shouldn't take it for granted that all your elements will be correct. And that's really what the Cook's distance plot is for. And then finally, if I come over to standards, this just gives a report of the results. So for each standard, we have our concentration, our prediction, our difference, and our relative change. And you can click on these to sort them as well. So obviously down here, our negative 262% difference between the prediction and the concentration means we've got some work to do. So let's first explore how to correct this. If I come over to Lucas Tooth, you'll notice the plot changes quite a bit, and the Calc curve you start to get kinks. That's because with a multilinear regression model, we start to get a little bit different of a calibration curve. What you'll see here will be a LOS between the points, but what you're changing is the normalization of those points. You'll also notice your R squared changes a bit. That's because the way we plot a multi-dimensional plot in 2 dimensions means we have to aggregate some variables, so you'll see a little bit of variation there. Next, we're going to normalize to Compton, and specifically a Compton range of, well, first let's take a look at where sodium is and make that decision together, shall we? So if I come over here, element sodium, sodium's way out here. Let's go ahead and zoom back out. Sodium is way out there. So what we'll want to do is choose a baseline that reflects the variation of sodium. I like to choose this flat area of the spectrum between about 0.7 to 0.9 keV because there's no elements that fluoresce there, and that'll give us a pretty flat platform to analyze these guys. So we'll go 0.7 to 0.9. Technically, we are not normalizing to Compton here. We're normalizing to the, and I apologize, my German colleagues tell me that I mispronounced this word, but we're looking at the Bremsstrahlung radiation, which is basically the random X-ray backscatter that occurs when you throw electrons against something dense. Now, for sodium, what we're going to be doing is we need to start adding some corrections. Now, first, now this is a little bit of prior knowledge. You're always welcome to ask an expert if you need information about what elements interfere with which. But for sodium, there are 2 elements that are going to cast what we call escape peaks. That's where the photon glances off the detector and leaves a little artifact. And that includes both chlorine and rhodium. Now, chlorine is probably not too high in these, but we'll add it anyway. The good news with intercept corrections is it's hard to break your calibration with them since they are linear scalars. They don't change the dimensions of the regression. And then of course, rhodium L-alpha. Now the instrument I used here had a rhodium anode, which means we're throwing electrons against a rhodium plate, which means rhodium is guaranteed to be in my spectrum. And I want to correct to that in particular. If you have a silver anode, you'll want to consider adding a correction for silver, but only on the elements it interferes with. In this case, I have the advantage of knowing that rhodium L-alpha overlap has an escape peak by sodium. So we'll add that correction in, and it's starting to look a little bit better. Next, I know if I go over to counts or to spectrum, this is sodium. The peak that is going to accentuate the fluorescence of sodium is going to be aluminum, magnesium, and silicon. Typically, aluminum falls a little closer to that sweet spot, so we're going to add a slope correction for sodium, and our calibration has improved. I can try it for magnesium too, but it's only an incremental advantage, so we're going to get rid of that. Now, my validation plot is looking a lot better. I've got an R squared of about 0.4, looks like we're really measuring something. But if I come over to my calibration curve, do you see how it bends back down? That's a big warning sign that I don't have a reliable model. If I come over to diagnostics, I can see that we're going to have a couple values that are falling far outside of the accepted model. So first things first, I'm going to take out a point here. And by the way, when you take out that point, that removes it from consideration for just this element. You'll want to be cautious with that, but it can help improve your models. Now, if I look, there's only a couple points here which are falling out as significant outliers. So we're going to pull those 2 out. We'll start with that one. All right. Let's Let's come back over here. And I don't like these two because they're bending my regression model down. So I can choose an area of the plot like here and click toggle, and that'll pull them out entirely. Now, our calibration has improved significantly, 0.8. If I come over to Diagnostics, these are looking flat. Looks like we're doing well. I think I'm pretty happy with that state of affairs. We can explore other corrections, so I can come in here and add silicon, improves it a bit. We can take off silicon and add magnesium, doesn't change much still. I think that's a pretty good calibration for sodium, given, and just so you know, sodium is very hard to measure with X-ray fluorescence. Its average analytical depth is going to be close to around 7 microns in the sample itself. So we're not really going to see it all that well with vacuum conditions, but if you are doing a helium flow, you'll probably see it a lot better. Once I'm happy with that, I can click Update and move on to magnesium. Now you'll notice all my standards come back with magnesium, but it does remember my normalization, which is good. But if I go back to sodium, the good news is it's going to remember your choices for sodium. So once you've committed it and click Update, it will commit all those to memory, and you can start off with a relatively fresh slate for standards and corrections with the next element. So first things first, for magnesium, if I come over to spectrum, I can see that magnesium here is very close to aluminum. So aluminum is going to influence that background. So we'll come over here and add aluminum, and that improves our model quite a bit. Next, we'll come over to rhodium L-alpha, add that as a modifier, and then finally silicon. So things are looking pretty good. What I can also do is come back over here. If there's a point giving me grief, take it out, and now we've got a very good model. You can check diagnostics if you'd like, but overall, we're doing good. So we'll click Update and move on to the next element. So aluminum is next to silicon. Now, for light elements, this is important because the K lines are not that far from each other. Once we get to heavier elements like iron and nickel and copper, it might not be as important to do that next element intercept, but don't take it for granted. Check your spectrum. So for slope for aluminum, I've got that. I could also add silicon as a slope value here. If it doesn't improve it that much, I'd go ahead and take it off. In general, the wisest words I've ever heard for building a calibration is that the best correction is no correction. So that's aluminum. I think I like it. We'll go ahead and update and move on to the next element. Silicon. So silicon looks good. I know that aluminum is next to silicon, so we'll want to add that as a correction, which improves it quite a bit. We could also add in calcium, but that actually makes it worse, so we're not going to want that. For slope, let's come down and we can look at adding aluminum as a slope coefficient. Nope, incremental change, we'll get rid of that, and phosphorus. It's a pretty good calibration. I think I like it. If I come over to diagnostics, I can see if there's any points falling pretty far outside my model. It doesn't like these two, so we can get rid of those. If I come over to cal curves, well, that improves it a fair bit, actually. Might get rid of that point there, and now we've got an excellent regression model. So we'll update and move on to phosphorus. Now, phosphorus is going to have a very specific correction you're always going to want to include if you have a silicon-based detector. And that is, my big line here, calcium, has an escape peak that's going to fall by phosphorus. In fact, if we take a close look at phosphorus here, you can see there's almost 2 peaks side by side. That's the calcium escape peak, just a little less than 2 keV. So what we're going to do here is we're going to add calcium as an escape peak. And that's just doing our due diligence. We also have silicon nearby, so we'll go ahead and add that adjustment. For slope, we'll do calcium since it's right on its absorption edge, and that improves things quite a bit. What else do we want to add for phosphorus? You know, I might be very happy with that. We'll let our Diagnostics update. I think we're good. Update, and let's move on to sulfur. Now, sulfur is going to be right next to rhodium L, so we're going to want to add rhodium L lines as a correction. We'll probably also want to use them as a slope modifier since they can excite. But if it doesn't change, don't do it. So that's sulfur. Calcium is going to be an influence in sulfur as well, but not that high. Chlorine, no change. Potassium, little change. So far, so good. Doesn't look like we're doing much to alter sulfur. We can also try changing its normalization. That doesn't improve it at all. 0.7 to 0.9. 0.9. What else can we affect sulfur with? Let me think. Sulfur looks pretty robust. So if you find that you can't do anything to change that particular element, we can call it good, you know, that point and that point. Let's try this. Let's see how that looks. That does improve it, so those three down there. We'll go ahead and update based on those changes, and we'll move on to potassium. Now, earlier I mentioned I don't have values for chlorine. That's fine, we just won't have a model for it. So potassium looks pretty good right out the bat. I do know that rhodium L beta is near it, so we'll add a correction to that. For a slope correction, I might consider calcium since it's a big element right next to it, but if it doesn't change much, don't fix it. So if I come over to diagnostics, looks good, might get rid of a couple of the worst offenders. And come back to Calc curves. You know, I don't want to take out points there, even though we're having some problems with them. You want to use your own judgment. Diagnostics only assume that you've done all the corrections you need. Iron helps it a little bit. Another option is if I come over to spectrum, potassium is going to be right here, which means I might want to consider normalizing over here. So let's do 2.5 to 2.8. That's much better, isn't it? You can see we don't have that many outliers. So here, normalization was a big improvement. So in this case, I'm happy. Let's click Update, and let's do calcium. Now, quick note, with normalization in the past, with most calibration software, you would choose one normalization for the entire calibration. In this case, we're making each normalization specific to each individual element. So by changing it for potassium, I have not affected the calibrations for sodium or magnesium or others that used a different factor. So let's come over, let's click Update, and let's move on to calcium. Calcium looks pretty good off the bat. I do know, however, if we come back to spectrum, this is the K alpha line for potassium. The K beta line does come close to calcium. So I'm going to add an intercept correction for potassium because it's such a close neighbor. It might not change much since we have so much calcium, but still important to do. For slope, we might consider iron, doesn't change much. Silicon, doesn't change much. I think we're in pretty good shape. Might consider that right there. No, we're good. Update, and let's move on to titanium. Now, titanium is a lot uglier than the ones we've seen so far, and if we come to spectrum, I'll show you why. If we go over to titanium here, this is the K alpha and the K beta line for titanium, but you see that that there are other peaks here mixed in with titanium. That specifically is the L line for barium. So to fix that, what we'll want to do is come over to Calc curves and add an intercept correction for barium, which improves things a little bit. We'll want to get rid of that value there. 0.9, doing much better. Diagnostics look pretty even, though those 2 points there are causing us grief. So next, what we're going to do is we're going to consider slope corrections. It's sandwiched between two big peaks, calcium and iron. Actually, iron doesn't change it too much. We'll get rid of that. But that goes quite a ways. Get rid of that point. We're at 0.97. Come over to diagnostics. Things are looking pretty flat. So I'm happy with that particular regression line. Update. Let's move on to chromium. Now, one quick note, we can do a calibration curve for elements like chromium and manganese with 15 kV, but we're going to have a lot of Bremsstrahlung radiation noise influencing us. So if we come back and zoom out, right now we're in this part of the spectrum. Let's go ahead and zoom in a little bit here. And so out here, normalization will be a little different. We'll want to consider changing this. One thing I like to do for heavy elements further out is we'll do 8 to 10 kV, which improves things a little bit. For intercept corrections, barium is going to come underneath chromium still a little bit. For slope, iron is going to be quite large. And then we can consider calcium as well. I'm skeptical it'll do much. Yeah, let's get rid of calcium. Let's go ahead and get rid of far out elements, and now we've got a decent calibration curve. But again, you'll want to measure at 40 keV with a filter to get best results for elements like chromium and elements like manganese, but we'll see what we can do. So first off, iron. If I come over to spectrum, let's choose iron. Well, first manganese is here. You can see iron is right next to it. So we're absolutely going to want to add iron as an intercept correction. So let's add iron. That improves it quite a bit. For slope, we may want to consider iron as well, just because it's right next door and it's exciting it. And then as an intercept correction, chromium comes right next to manganese. So we'll want to include that as well. If these points are causing us grief, we can get rid of them. And we've got a tighter model. Next, let's do iron. Now, iron right off the bat looks pretty good. For slope, I may want to consider calcium, though it doesn't change anything. Let's get rid of it. Let's just take out the 1 point that's driving us a bit further. Double check diagnostics, and it looks pretty good. I might get rid of that point there. There. All right, let's update. And then finally, barium. So barium's not looking so good, but remember, if titanium was influenced by barium, the reverse is also true. So let's add an intercept for titanium. Let's add slope coefficients for iron and calcium. And now let's take a look at, oh, barium, by the way, if we come back over here to spectrum, is down here. So correcting our normalization should probably be revised to 2.5 to 2.8, which is the rhodium L line. So that's our intercept with titanium influence. There we go. So titanium is a slope correction, helped it quite a bit. Looks good. We'll click update, and that's actually all of our elements. So now, if I click save, that commits all the calibration changes. So now all the model elements are all saved together. And now if I click model, it's going to download a new calibration file right there. So we're going to go ahead and add that here to my home folder. So that is our new calibration folder. So if I want to use that calibration on a new data set, I can come over to apply calibration and we can grab it. So that was in my home folder, T4S 1864. We will load that. Then I'll come over here to choose spectrum. And let's just grab some random spectrum just to see how this looks. So we're going to go, actually, you know what? We can do even better because we've actually used this data on a project. So that was in calibration spectrum. This is a project at Brigham University. We're going to grab some spectrum from a site in Turkey. So this is taken with 15. This looks good. Are these guys all 15 kV? These guys all look like 15 keV. Excellent. So from the site of CloudCal, we'll choose and grab those guys. Click quantify. And we should have our quantitative results. So this gives us results of our analysis. So we can take a quick look. We see calcium's around 7%. Silicon is not looking good. Aluminum is 16%. If I come over to counts, this gives me my counts as well. If I am not happy with a result, so let's say my silicon numbers look really bad, for example, that can be because I've got a bad curve. If I come over to silicon, it remembers all my changes. We can, for example, get rid of an intercept. Update. Save. Download that model. So this is in the event I wanted to change something. Come back over here, replace, apply calibration. We can load up that new calibration model in my home folder. And so once we change something, that'll change our numbers. So that gives you a quick example. So you can quickly update your calibration and make changes as you go along in that manner. Now, let's say I want to start all over again. So we're going to start all over. And I decide I want to change my calibration. I can come down here to load calibration file, grab that file, click use cal file. That's just the signature to use that particular piece of information, and process data. If I come over to counts, it's remembered all my elements. We come over to concentrations, enter those values. We come over to cal curves. It remembers your choices from your corrections to your normalization to the individual points you have chosen to get rid of. So we can at any point change our model if we run into problems. You can also add new standards. So for example, that was instrument T4S 1864. Let's say I wanted to change that to a new instrument. So if I come over to calibration spectrum, let's grab a new instrument, T4S 1130. Actually, let's grab Mike Dobby's instrument, T4S 2331. So we come over here. We have his standards right here, which unfortunately are not organized near as nicely as the other ones. We're going to come over here and grab them individually. And if you make a mistake, don't worry, you can just come back and reopen them up. So major, 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 major. So in this case, the file names indicate the light element versus heavy element quality of each of these. Major, 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 and major. So grab those guys. Now you will want to make sure they're the same number. I can click process data. We'll go ahead and say Mike Dobby's tracer, process data. I'll come over to counts. Now this is the counts from the calibration file because I've chosen use cal file. If I come over here and change it to use imported spectrum, it brings in the data from Mike Dobby's instrument. So now we've got spectrum from one instrument, but all the calibration corrections from another. If I come over to add concentrations, it remembers those, enter values, cal curves, and what you see here is it's updated it. So if I click update there, I could just pro forma go through and update. All these calibration curves are for a new instrument. In case you're curious about that, if I click update, this was for aluminum. If I come over to counts and I the original data, if I go to cal curves, you'll see the cal curve change based on the old data. So you can use this to compare two different instruments and update their calibrations. So we'll come over here, update, but you do have to go through each and update it. That is important. Update, 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 update. So far, everything looks good, which should be the same. These are the same physical standards. They've just been measured on two different instruments. Update. And of course, any changes you make here will only affect the new instrument. So for example, if that standard had a contaminant, we can get rid of that. Update, come over to iron, update, and then finally barium. Update, save, and now we've got a new calibration file for Mike's tracer. So this just gives you a rough overview of how we can build a calibration, apply it to new data, and how we can use an existing calibration to either modify it or modify another instrument. If you've got any questions, please let me know. But this should give you a quick overview of the new software features that are available. Now, one note is by designing a calibration curve and by designing a new calibration file like the .quant file, which is the extension we're using, just a moment, the .quant file, we can actually apply this calibration to other software we'll be building. So in the long term, we've got, or in the near term, we'll have a core analysis app where you can apply this quant file to a sediment sequence and plot along that. We'll also have an Obsidian sourcing app, which can then be generalized to ceramic sourcing. In general, though, you can basically build and custom design your own calibration files. The most immediate benefit of this is you now have an ability to do empirical calibrations on a unit using an open source platform. In any case, thank you very much. And if you have any questions, you're welcome to contact me. And yeah, good luck and happy calibrating.